eTech49 is a strategic advisory business specializing in disruptive technology in power electronics, machines and drives for autonomous, connected and electrified vehicles and machinery. This video discusses the motor technology commonly found in electric and hybrid vehicle powertrains. In this video, we will focus on permanent magnet radial motors. There are also switch reluctance and induction machines, but these are deliberately excluded. In a radial flux motor, the magnetic field is radial to the rotational axis of the shaft. There are two key topologies and several subclasses within that. In this type of motor, the rotor spins inside the stator. Avid has extensive design and volume manufacturing experience of all types of radial interior rotor motors. The first kind of internal rotor motor we're going to look at is known as a surface magnet or SPM motor. In this type of motor, the magnets are mounted to the surface of the rotor, typically bonded in place, held in position by a composite tape or manufactured as a ring that is wrapped around the rotor. This style of motor is used in a wide range of applications where high efficiency is required and also for high-speed applications. This style of motor is typically highly efficient because the torque is generated directly by the reaction between the magnetic field of the surface magnets and the fields generated in the stator teeth by the windings. There are minimal rotor losses as the magnetic field from the magnets is directly acting in the air gap. The key disadvantage of this kind of machine is a relatively high proportion of magnetic material for the torque of the machine compared to other types of motor, and the increased manufacturing costs, especially when considering filament winding to provide a high strength retention of the magnets. The second kind of IR motor is known as an interior magnet or IPM motor. In this style of motor, simple bar magnets are slotted or moulded into punched holes in a rotor core manufactured from a stack of steel lamination sheets. IPM motors typically use less magnetic material than an equivalent SPM motor, reducing costs. The magnets are also mechanically located in the slots, removing the need for any banding. In addition to the magnetic field generated by the permanent magnets, they also typically use rotor reluctance to enhance the magnetic field strength at the surface of the rotor. Whilst this improves the torque to magnetic material ratio, it reduces peak efficiency under high torque when compared to SPM rotors. Although no banding is required, the assembly of the rotor can be complex due to the use of multiple layers of lamination steel and magnet arrays. The need to insert many small magnets into the slots requires complex automated machinery for volume production. IPM motors are popular for electric vehicle traction applications. This motor is known as an external rotor or outrunner style motor, sometimes shortened to ERPM. In this style of motor, the magnets are mounted to the interior surface of the rotor, typically bonded in place. The rotor spins outside the stator, which is fixed inside the rotor. ERPM motors provide more torque at lower RPM due to the improved mechanical advantage offered by the rotor-stator configuration of the active magnetic surface when compared to an IR motor. This makes them well suited to certain applications. The weakness of an ERPM motor is the difficulty cooling the stator and rotor compared to an IR motor, where there is a good thermal pathway from the stator to the motor housing. On the ERPM motor, the stator is inside the machine with no thermal pathway, and it's difficult to route liquid cooling into it. Sealing of the ERPM motor assembly is also more difficult, as the moving part is external to the stationary part, which typically means that two sets of clearances need to be maintained in a housed motor. Finally, the rotor has a relatively high inertia because the rotating mass is mounted far away from the central axis. Unlike a radial motor, axial flux motors feature a magnetic flux that runs axial to the rotation of the motor rotor. They're sometimes called pancake motors due to their flat shape, which is possible because the active magnetic surface is the face of the rotor rather than its outside diameter. This allows an increased active magnetic surface area compared to a radial motor, and typically improved performance in terms of power to weight and torque density. There are two key axial flux motor configurations: internal stator external rotor and external stator internal rotor. The internal stator external rotor axial flux motor, sometimes called a torus axial flux motor, has several key advantages. The benefits of this type of motor are compact stator windings that are easy to mass produce and reduced motor copper content. However, there are some significant disadvantages, which include often complex rotor forms leading to rotor stability issues and requiring complex control. These machines have a high rotor inertia. It is often difficult to cool the motor, requiring separate oil cooling systems that negate some of the power density benefits of the motor, and it can experience high levels of torque ripple from the segmented stator. The double-stator, single-rotor axial flux motor, sometimes called a DSIR, is one of the most power and torque-dense motors available on the market. The benefits of this design stem from the simple rotor, which is very stable and compact. It has a reduced rare earth magnet content compared to most other PM motors. It also has a very large heat rejection surface area from the rear faces of the motor stators, meaning it is easy to cool, which delivers good real-world performance and high usable power and torque density. The housing is also easy to fully seal, which makes it ideal for harsh environments such as electric vehicle drives, hazardous area robotics, and aerospace. Avid's patented Evo machine also has an ultra-low inertia composite rotor. This can significantly improve transient performance of this motor. The key disadvantage of this style of motor is an increased copper content compared to an ERAF motor and the need for slot-inserted stator windings, meaning high-volume manufacture requires some very specialized machinery. Here we can see the sizing equation for a radial flux motor. The torque density stays the same for a given length of machine. It can be seen that the radial machine increases its torque to the power of 2 of the diameter. Power density then comes from torque density times speed. Here we can see an axial flux sizing equation. For a given axial flux motor length, it can be seen that the axial machine increases its torque to the power of 3 of the diameter. As the diameter increases, typically the max operating speed is reduced. This graph shows how the sizing equations work in practice. The graph shows how torque and power vary when a radial and axial machine of originally 150 mm diameter with the same performance have their diameters increased. It can be seen that as the diameter increases, the power and torque of the axial machine increase much more than in the radial machine, which is what leads to the higher torque density of axial machines. Axial and radial flux motors have their advantages and disadvantages, meaning they're both suited to a wide range of applications. Deciding which type of motor will perform best for a particular application requires a more in-depth study of the application requirements. Thanks for taking the time out to watch this video. If you have enjoyed it, check out our channel and other content, including our 5-star rated podcast. To find out more about how eTech 49 could help your business, contact us today.